see the pattern? So the explicit formula for this sequence would be n over, and then the common difference is 2, so 2n, and then adjust. If you plug in 1, you want to get 6, so plus 4. And what would be the limit of the sequence? That's right, 1/2. So if I keep on adding these numbers forever, you will get exactly 1/2. Keep on going. Okay, this looks like a repeat problem. Let me look. This is exactly the same problem. 6D, throw away. Okay, E. Oh, here's the interesting tidbit. Cosine n degrees. Okay, let's look at our unit circle. And this one, since it's trig. If I plug in 0, notice you start by plugging in 0. You get cosine of 0 degrees, which is, oh, this is ugly, yeah, right there. What's the x-coordinate of that point? 1, right? And then you got all the degrees in between. And of course, cosine of 90 degrees is 0. And then you got all of these until you hit 180 over there. Cosine of 180 is -1. Oh, so 1 cancels -1. But then look, what about 1 degree and 179 degrees? Don't they cancel out too? Right? Because cosine is the x-coordinate. The x-coordinate there is the opposite of the x-coordinate there. They cancel out. And so everything in between is going to cancel out, right? The x-coordinate there cancels the x-coordinate there. So you just get 0. Okay, number 7. Now, we know what sigma notation means. What does this pi notation mean? And this is capital pi. Obviously, I wrote this in 2002. So, n over n plus 1. Well, you pretty much do the same thing. You start by plugging in 1, and you're going to end by plugging in 2002. If you plug in 1, you get 1/2. You plug in 2, you get 2/3. You plug in 3, you get 3/4. And you just keep on going until you plug in 2002. So you get 2002 over 2003. But instead of adding them, that would be sigma. This is pi. You multiply them because that's the Greek letter for P, which stands for product. You multiply these numbers. Woo. And then what happens? This cancels that. This cancels that. This cancels that. So the only thing that's left is 1 over 2003. Wait, yeah, there you go. I just want to expose you to the pi notation. But of course, when you go to college, you can say, Mr. Parker never taught me that. 8. Okay, a jar. Oh, here we go. A jar. This is the last problem. Hallelujah. 3 red and 2 black marbles. Bert and Ernie take turns drawing marbles from the jar, noting the color, and then returning the marble to the jar. That means with replacement. The first person to draw a black marble wins the game. If Bert goes first, what's the probability that Ernie will win? Okay, well, what's one way Ernie can win? Bert goes first, and he pulls out the red, right? Black to win, right? Hey, let me read again. Yeah, black. So, what's the probability that Bert gets a red? 3/5. And then Ernie now pulls out the black. 2/5, right? Because you're putting the marble back in the jar. But is there another way he could win? Yes. Bert could go first, get the red. Then Ernie gets the red. Then Bert gets the red. And then Ernie pulls out the black. Yeah, but Mr. Park, this can go on forever. You're darn right. So Bert gets the red. Ernie gets the red. Bert gets the red. Ernie gets the red. Bert gets the red. And then Ernie pulls out the black. And like we said, this thing goes on forever. What is the meaning of this travesty? Well, it's an infinite geometric series. What's the common ratio here? What do I need to multiply this by to get that and then that and then that? That's right, 9/25. That's the common ratio, and the absolute value of that is less than 1, so we can use the formula. First term, all over 1 minus r. There you go. That's how you add. So actually, this problem is easier than if it actually stopped. And then, can I leave the simplifying to you? No. Multiply top and bottom by 25. So 6 over 25 minus 9, which is 6 over 16, which is 3/8. Infinite geometric series. Hey, we did it! We did it! We are done. Goodbye.